Yeah, if you've been following these videos, you'll probably be expecting us to talk about the setup of the problem after the meshing. So this is video number 4. And we're in ELMER GUI, and we've got the mesh, and the various parts of it have been set up using the Salome, and then it's been meshed in Salome, and we took some care over the different bodies and the boundaries and so forth that we'd have available to us. If you don't take care of that, then you don't have these bits here. So we're in ELMER GUI, just in case you haven't already figured that out. If you can't see this panel at the side, excuse me, it's Show Object Browser. This is 8.4. Doesn't actually say. Well, it is 8.4 anyway. Unusual. Open source software almost always has all the stuff here about the version you're in. Anyway, there we go. This is 8.4 release, which is the latest stable version at the moment. And it's August 2020 at the minute. So we've got 4 bodies, and we've got 2 boundaries. One is the outside, and this is the rest, which is, I'd never actually, I didn't explicitly create a group, a mesh group for these. When we converted the mesh using ELMER Grid, this will have been created, but we're not actually going to use it. We have to add equations, materials, the stimulus, which is a body force, any initial conditions, and the boundaries. Excuse me. So we'll go through one at a time. Starting off, let's just double click that. Okay, so that we can set them here, but first of all we have to set everything up. So equations, and you click add. That's it. Equation 1. Sure. We'll call it MGDYN2D, which is what it is, but you don't have to call it the same as what you're gonna, the model you're gonna use. You can call it whatever you like. First priority is the only thing we're going to use, so it doesn't really matter. One thing we could do is name the bodies. That might be fun. We want it to apply over all the domains, or over all the regions, if you like. So you can see that I'm unchecking and checking. As for the solver, I would probably choose to solve this direct and with mumps. The only problem is I know I haven't got mumps solver installed, and because I didn't compile the version of ELMER that I'm using at the moment, it's the Windows compiled binary. It's not that easy for me to get it, and I don't know, maybe I could, but anyway, for the sake of simplicity, and because I know for sure you'll have this iterative solver, we'll use this one, even though it's not going to take that many iterations to solve. We could go direct and it'll be a bit quicker, but it doesn't matter. As for the rest of the solver options, I'm going to leave them as they are. Only thing we need to worry about here, so this is the solver options for the Magnetodynamics model, Magnetodynamics 2D model. We need to just keep in mind that variable name. You can change it if you want, but I'm going to leave it at that, and I'll need that in a bit. We will always run it, so that's effectively saying I'm going to run every time step. Not before the time step, not after the time step. As part of each time step, we will solve this model. If you're doing post-processing, obviously you might do it before saving. If you want to change your tolerances and so forth, you can. If you've got lots and lots of processors available, you can use Hyper, which is a system of parallelization. You can do all sorts of adaptive grid and type things as well, but we don't need to get into any of that at the moment. This is a simple problem. So there's not much to do there. I'll update and OK. Let's just see if we can rename this. I can. Good. Right, who are you? You're coil. You know? Sometimes, if you're careful with your naming, you can have the ELMER grid preserve the names between Salome and ELMER GUI, but in this case I think it's because I put spaces, but I'm not sure about that, so don't hold me to it. So that's what they are, and this one we'll call the... Oh, just want to change its name. You're not going to let me, are you? Okay, never mind. So if we go into... I'm going to close that from next. It's a little deceptive that it's there. Really, I need to set this lot up, then I'll deal with that. So we've got Magnetostatics 2D, it's active. So now these have changed because I've renamed them, which is fine. The other thing I need to do is turn on the post-processor. Now, it used to be the case that you would choose Magden 2D Post, and the thing it would call is called bsolve. But if we look in the models manual and we scroll down, down, computation of magnetic fields in 2D, and we scroll down some more, a little more. Keywords. Let me just check the sound. Sound is on? Good, sound is on. Go back here. So this is the 3rd of August 2020, this document. Note, the subroutine bsolver described here is obsolete. It is recommended the subroutine Magnetostatics calc fields within the module Magnetostatics is used for post-processing. So, this is new in quotes. I don't know when that was actually changed. It may be that it's been changed for years. But I spotted it anyway. So, that was the one. Call it 2, it applies across all domains. General, before saving. Everything else I leave the same. It's nothing else. Oh yes, calculate the magnetic field strength, electric field. Yeah, we'll let it have a go at those two because you should be able to get this one because we're enforcing it. If it gets that wrong, then woohoo. And we obviously want the magnetic field strength because we want to get B effectively. We're not really imparting any forces on anything, so we don't need the Maxwell stress tensor. We are not going to do anything like induction heat or anything like that, so we probably don't need to worry about dual heating. I think we can leave the rest as is for now. What else do I want here? Not much. Update. Okay. Materials. We need a couple of materials. So we'll have this one's going to be material 1. We'll put the library ones in first. So we've got air. Applies to air clearly. Okay. We need copper, which applies to coil and current. Since we are enforcing current density and we're not too bothered about the voltage drop across these two regions, or the potential difference, sorry. It probably doesn't matter if we don't specify it, but the solver might get upset if we don't. And then we need to add one of our own, which means we need to get a model for our ferrite, because I don't think there's a model for a ferrite in here. Maybe there is. Doesn't look like it. Good, because I did that last time, so it'd be a shame if I'd messed up and it was there. So we're going to call it N87, because that's what it's going to be. And we're going to make the electric conductivity 0, which is not strictly true, but it's not too far off. Relative permeability is probably about 2,300. It only applies to the core because that's all that's left, but we will specify BH curve. Now, if you look at the model manual, you will see it says you need to have spline coefficients. I presume you put the coefficients in as pairs, but as it is, I want to bring in a file. So I need some extra lines of code in the CIF file to do that, to allow the solver to use the file that's got the data for the BH curve for the material, rather than putting parameters in here. So we'll have to have a look at that when we look at the CIF file. Otherwise, there's not much doing, so we can OK that. Let's just save this before it crashes. So we've got inner coil has Magnetostatics 2D, is made of copper. Outer coil has Magnetostatics 2D, is made of copper. We've got air, which has Magnetostatics 2D and is made of air. And we've got core, which is also got Magnetostatics 2D being solved on it, and it's made of an 87. So core, air, coil outer, coil inner. Cool. We need to add some body forces. We're going to have body force on coil inner, and we're going to choose, if you like, doesn't really matter. Let's have, this is coil inner, minus 1E3, that's amps per meter, amps per square meter, amps per square meter, we call that, current density inner, and this one will be, no! Oh Lord, really? Yeah. Is it the end? Hold your breath and count to 10. Oh, that's a shame. Hopefully we didn't lose much. I had just saved it. Cool. Yeah, so the only thing I'm missing is this body force. Cool. Breathe. Oh, come on. Surely not. Well, that's interesting. There's definitely a bug report here somewhere. Gotta be. Just need to wait for this to give up. Okay, let's have another go. Right. I'm convinced I clicked that, but never mind. Choose that one. Current density minus 23. So I don't know. Okay. Oh. Cool, so that's positive. That's negative. Cool. Because they can't be the same, because if they are, then they'll cancel each other out. Initial conditions, we don't need to add anything. The only thing we could add is a constant Z orientated, which is in or out of the page. Magnetic vector potential, and we don't want any at the start of the problem anyway. Boundaries, only one to concern ourselves with, which is that one, and it is on boundary 5. Let's just call it boundary condition 1. It's not like we're going to mix it up with anything else. Save, save. So, things that are outstanding at the moment. 1, we need to go into the CIF file and explain to the solver that we intend to pull in a file with the BH curve data in it. Second thing that's missing is that when the CIF file is generated by ELMER GUI, it's going to miss out one line, which took me a bit of hunting around in the forum to figure out that it was missing it, and I suspect it's also a little bug, and I rather suspect that this change, the obsolescence of B-solver in favour of the Magnetostatics calc fields from the 3D solver, is a relatively new thing, because if it wasn't, then the bug in ELMER GUI, that's not really a bug, it's a missing line in the CIF generator. Somebody would have figured it out and solved and changed the code and pushed it to the repo, but it hasn't been done. Either that or I've cocked it up somehow. But anyway, we need to add a single line in to explain to the solver what the vector potential is that we want it to do the curl calculations on. So we've got two things to do. First thing of those is fairly straightforward. We need to get some data for N87. So I have somewhere, maybe I didn't save it. I didn't. Is it in here? No, it isn't. Okay, internet it is then. N87 material. ERIAL. Is that the one? It is. We'll take this graph. So this is for 100 degrees C. Chances are magnetic's going to be hot when it's running. It might not be 100, but could be. It's certainly not going to be 25. So a bit of zooming in and touch the old print screen, and we can pull that into paint.net, which you can get on Google. It's free. Let's make this a bit bigger. Tools, where's the tools? There's the tools. Nick this, copy. Right, this is Engage, which you can obtain from here, github.com/mark_mitchell/engage-digitizer, that bit. It's a program for making CSV files full of data out of bitmaps and such like, and it's a really handy thing to have, especially if you're in the midst of your PhD and you've got some data from a paper from the 1980s and you need to compare it with the data that you've just generated to see if your hypothesis is good and you're going to get your doctorate, or if your hypothesis is rubbish and you're not going to get your doctorate, or if, as is very likely, the Germans got there first. You can insert whichever country you wish. Japanese, Chinese, Koreans, doesn't really matter. I'll tell you who didn't get there first: the English. All our firsts are in the past. So, there we go. This is one that I made earlier because I don't intend really to go off on an engaged thing, but essentially you set up some axes and you explain to it what the axes mean, and then you click some points and you export it. Having exported it, you'll end up with a file that looks a bit like this. It might have a couple of lines in the top that you have to delete the header, and you might have to make sure that that is actually a space and not a tab. But besides those things, that's where we're at. So this is B in Tesla, and this is H. Oh my god, I'm so sorry. This is H in amps per meter, and this is B in Tesla. Not forgetting, of course, that this is B in millitesla. But since I told it when I did the coordinates, I told it an answer in Tesla. It's 0.4 as opposed to 400. Good. Got to get rid of that other point now. But anyway, so that's my method for pulling the data for the BH curve. And we will now have to tell ELMER about the BH curve, and we also need to add this line into the CIF. So we'll save everything, and we'll generate the CIF file, and then we'll edit it. So, to save embarrassment, what I'm going to do is I'm going to open a CIF file that I've already made these changes to, and then we'll have a little comparison. I thought that plan was going to go well, but never mind. Right. You just go away for a bit. There we are. So we have, much of it is the same. So, solver 1 is mag_dy in post, and is the arrangement of the file is slightly different, but that doesn't matter. We need that line. It's missing from here. It's not there. And when I said earlier, I can change the name of this potential. It was in, I don't know if I can show it easily at the moment, I can't. But if you skip back, when we were discussing the equations that we were going to put into the model, I clicked on one of the tabs and said this variable is called potential, you can change it if you want. If you did, then obviously this has to change as well. So I will drop that in here. Doesn't actually matter, I don't think, where you put it inside this block. I would imagine these are mostly the same, so you can change them. If we don't put that in, what will happen is when the solver is finished doing the calculating the vector potential, and it moves on to calculating the B field, H field, current density, that sort of thing, the solver that does that extraction, which is the model, which does that extraction, won't know where to look for the data it needs to do the extraction on. It won't be aware of the other set of data that's been produced. So that, I think, is probably a little bug in ELMER GUI because that line should be pulled in. Other thing we need to do, if we go up to, down to, here we go. That bit. HB curve is variable called non-len, which is a real cubic monotone spline, although the word spline doesn't appear, and is pulled out from a file which is included called na7curve.txt. That little chunk of text took me an age to find, and I got it from the forum, which is where help comes from. So we need to drop that into material 3. Well, into this one. Oh, that's interesting. That looks like copper. I think I must have copied copper. Did I? Young's modulus for copper. Oh, maybe not. Yeah, I did. Okay. I'm going to delete that lot now. Drop this in instead. I think it's actually a bit more than that. Cool. Save. Now, got a case of. Yep. So, obviously, I didn't sit around in Notepad++ working out what changes I wanted to make. I ran it, it didn't work. I edited the CIF, I ran it, it didn't work. I edited the CIF, and so forth until I'd figured out all the errors. Having saved that, pretty sure I just saved it. If we now go back and do CIF generate, it will overwrite all our stuff as far as I'm aware. So you've got to be careful now. If you make changes here and regenerate, you have to go and add those lines in. Let us save everything and try and run it and see what we get. Of course it doesn't work. Why would it? Crazy to even think it might. So obviously I haven't actually included this file because it's still saved in my test directory. So let's put it in the directory I'm using for the video. Okay, now it's saved in the right place. Let's have another go. That is good. That's good, I think. The key thing is it's solved and it's converged. The fact that this one isn't doing much is I don't think, a significant problem. The key thing is that the model that solves, or the solver is solving the way Maxwell's equations are modelled in this model, and it's converging. And it's converged in 3 iterations, which is that's how I do it direct. So I can close that. You can read all this stuff if you want. If you're struggling for convergence, you will have to read all this, but the important thing is that it doesn't throw out errors, and that it does say I'm saving the things you're asking for, which it is. Obviously you can save it and pick over it, and if you've got problems and people on the forum want to see it, then you should have saved it so that you can show them. So we can leave this now and go back into Salome, and I will go into Paraview. I think we'll do this all in one video because there isn't very much that I want to say about the result. The result isn't terribly important. It's the overall method that's interesting. So this is in that directory and in video inductor, and I'm looking for the VTU. Okay. So initially it shows you nothing, which is a little disappointing. Kind of hoping it's just going to flash up with obviously correct result, but that's not how it works. I don't need that one. We leave the rest. Apply. Well, the right geometry's appeared, so that's useful, but we're still not actually looking at anything. So we've got to, we're probably going to look at surfaces, and we want to ask it for, let's have the flux density. Now, this is very promising. Very promising for two reasons. One, it's pretty much the same answer I got before, which is desirable. Second thing is, all the flux is in the core, more or less, except for some fringing flux around here where we know there's an air gap. If you found a lot of flux elsewhere, you'd obviously be thinking, well, this is wrong. Other thing we can do to have a look and see, does it seem believable? Is it the right flux density? I don't know. I need to go and work it out. How will I do that? Well, you can't solve this problem analytically, but I wanted to do an interesting, or at least a passably interesting problem. So what I'll probably do is I will make believe that this box is a single point there with the current density that's in the box flowing and another one there, and then I will numerically, using octave, create a set of an array or matrix of points, and I will work out the magnetic vector potential at each point due to this point current density, these 2 point current densities. I will use superposition to determine the overall magnetic vector potential on each point in my array, and then I will take the curl operator and get the B that way, which is pretty much what the finite element method is, except I will do it by hand using MATLAB or Octave or whatever. Haven't got round to that yet. To be honest, I'm not too bothered if this answer is wrong. I mean, if it is, it means I'd set something up in the simulation wrong, but what I really want to demonstrate is the workflow, and I'm pretty sure the workflow is solid. So let's pretend the answer is definitely right. I'll check it later. If it's not, I'll publish a retraction. Does one do that with videos? Maybe. You can have a look at the H field. Good, it's there. You would expect all the H to be in the gap. We can look also at the current density. That's where we injected the current, or where we determined the current density would be, and it's also the value that we determined it would be. If you're worried that they're both the same direction, it's only because we've got the magnitude up. If I look at the Z is into the page and out of the page. So I've got one is 1000 amps per square meter, the other is minus 1000 amps per square meter, so that's good, because this is supposed to be a coil. Right, that's more or less it. We have a result. There are some things that you would probably want to do differently. You would certainly want a mesh refinement around here. There's a good chance you want to put a cut line in. Maybe have a look at the B on the corner, so you might want to cut line across there as well, because that's where your saturation is going to be, and there. You probably want to have a look at the total stored energy so that you can work out the inductance. So there's a lot of other things we can do. Most important thing that I would like to do, other than know if it's right or not, which I'm pretty sure it is rather than setting a current density, we'd like to have a model for a circuit or a coil, and we'd like to be able to use so dynamic systems where we have a time varying voltage applied to the coil or a time varying current impressed on the coil, such that we can look at the time evolution of the B, and we can work out what the losses are. So we might choose to use a Fourier series approximation of the Steinmetz losses, and we can work out the total heat generated using realistic switching waveforms. And once we have the total heat generated using realistic switching waveforms, we can break out ELMER's heat transfer models, and we can remesh the structure in such a way that we concern ourselves with how much heat is lost from it into a realistically sized enclosure. And if we really want to, we can put a fan, and we can do some CFD, and we can go nuts. Or not. Depends how much time you've got to kill. Maybe we can have 2 fans, and we can work out the speed difference, and we can get the acoustic beat frequency, and we can work out if the person sitting in the room with the equipment will be annoyed by the... No, let's not go there. So you can really get carried away with it if you want to, but mostly that's what we want. This you can do in FEM, and if you haven't seen FEM, I've got a video about electrostatics in FEM. FEM's really, really good. It doesn't take 4 or 5 videos to explain it. You can do it pretty quickly, and it can do this, but it can't do time evolution with realistic looking waveforms. You can do time harmonic simulations where it's all sine waves, and you can do that in ELMER as well. So there's a few things outstanding. A video on how to construct the coil effectively and to run up some realistic looking switching waveforms, how to calculate the inductance, how to deal with how much energy is stored, how to deal with losses, loads and loads of things that we need to talk about. But in terms of getting to the point where you can simulate some magnetics, then I think we are there. Oh, we didn't look at the magnetic vector potential. Have a quick look. There. Sorry, hang on. Yeah, it's because I've got that one and that one the wrong way around. Wish I could invert that. The colours are a bit odd. Pretty much orange is none, and so is red, and the blue is the interesting bit, but it's backwards. I wonder if I can turn it round. Nope, still red on that side. Sorry. I'm not going to go back and resolve it, but if you saw in the beginning, I had in the first video and the second video maybe I had a plot like this. It looked the other way, where it was blue almost everywhere and red in the middle, and it felt a lot better. But it's only because I determined that this was in and that was out of the page, or this was out and that was in. It makes no difference. I could change the colours as well if I needed to, but that's the one that we're used to looking at, which is the flux density. Right. Oops. Come on, you. You? No. There we go. I thought mouse scroll would zoom. It doesn't. Oh, we're doing that, are we? Okay. Rightio, good. Well, there we are anyway. You can also see the mesh points there. In fact, you can. So there's the mesh. So not very well meshed in this region here. That's interesting. We never did in the mesh model, mesh video. We never did how to look at if the mesh is any good or not, did we? I wonder if we could do that quickly. Click, so it's highlighted. Right click. Got to be in mesh first of all. So I've just changed up there. Controls. Face controls. aspect ratio. That it? No. That's it. So in an ideal world, they'd all be nice triangles, either bigger or smaller, and you really don't want things like that where they're really odd shape. But that could be worse. Righty. So if you have an undergraduate thesis project on ELMER, don't email me. I'm too busy to answer. But if you need help with some magnetics design for industrial or automotive applications, or defence applications if you want, then I can certainly help you out. You can drop me an email, james@bearinstruments.co.uk, or you can have a look at our website, it's bearinstruments.co.uk, and you can roll your requirements in our direction. See you later.